Look down. What do you see? Perhaps grass or concrete or pavement, but beneath it all there is soil. Just dirt, you might think, yet this humble material is the very bedrock of our civilization. It supports our tallest skyscrapers. It cradles our deepest tunnels. It forms the pathways for our roads and railways. Without understanding soil, our grandest engineering dreams would remain just that, dreams. They would sink, slide, or simply collapse into dust. This crucial understanding, this science of the ground beneath us, is called soil mechanics. It is a universe of complexity hidden in plain sight. Soil mechanics is a vital branch of civil engineering. It delves into the physical properties of soil. It explores how soil behaves when forces are applied to it. Think of a giant building pressing down, or the immense pressure of water against a dam. Engineers use soil mechanics to predict these interactions. They design foundations that can safely carry immense loads. They build stable slopes that resist the pull of gravity. It is the science that keeps our built world standing strong. It transforms mere earth into a reliable engineering material, a partner in our creations. Long before textbooks and laboratories, humans were interacting with soil. They were building shelters, cultivating land, and creating pathways. These early builders were the first soil engineers in a way. They learned through trial and error, a harsh but effective teacher. A hut that sank into soft ground was a lesson learned. A retaining wall that collapsed taught them about earth pressure. This accumulated knowledge, passed down through generations, formed the earliest understanding of soil behavior. It was an empirical wisdom born from necessity and observation of the world around them. Imagine the construction of ancient cities, or the terraced fields carved into mountainsides. These weren't random acts. They required a profound, if unwritten, understanding of the Earth's properties. Builders selected sites with stable ground. They learned to drain water away from foundations. They recognized that some soils were strong, while others were weak and treacherous. This knowledge was woven into their construction practices. It was a practical science, focused on what worked. The magnificent structures that survive from antiquity are silent witnesses to this early, hard-won expertise in dealing with the challenges posed by the ground. For centuries, building on soil remained largely an art form. It was guided by experience and tradition. Then came the Age of Enlightenment. Science began to systematically unravel the mysteries of the natural world, and soil, that everyday material, started to attract scientific attention. One of the first to shine a quantitative light on soil behavior was a French physicist and engineer. His name was Charles-Augustin de Coulomb. You might know his name from the laws of electrostatics or friction in physics. His genius, however, extended beneath our feet. In 1773, Coulomb presented a groundbreaking paper to the French Royal Academy of Sciences. It wasn't about stars or atoms, it was about earth pressure. He was thinking about military fortifications, about retaining walls holding back soil. How much force does the earth exert? How steep can a slope be before it collapses? Coulomb approached these questions with the mind of a physicist. He proposed a theory to calculate the lateral pressure exerted by soil. He introduced the concept that soil strength comes from two components, cohesion and internal friction. This was a revolutionary idea. The seeds sown by Coulomb began to sprout in the 19th century. The Industrial Revolution was in full swing. Railways were cutting across continents, canals were being dug, taller, heavier structures were being envisioned. The need for a more refined understanding of soil behavior became increasingly urgent. Another brilliant mind stepped forward to advance the science. This was William John Macquorn Rankine, a Scottish civil engineer and physicist. He was a polymath, contributing to thermodynamics, engineering, and even music theory. His intellect also turned to the earth. Rankine, working in the mid-1800s, expanded on Coulomb's work concerning earth pressures. He developed his own theory, now famously known as Rankine's theory of earth pressure. Like Coulomb, he aimed to predict the lateral forces that soil exerts on retaining structures. However, Rankine's approach made different assumptions about the soil and the interaction between the soil and the wall. He considered the state of stress in a soil mass when it's on the verge of failure, a concept called plastic equilibrium. This provided engineers with another tool, another perspective. Section 5. The bedrock of modernity, Terzaghis revolution. The early 20th century witnessed the true birth of modern soil mechanics, and one name stands above all others in this transformation: Carl Terzaghi. Often hailed as the father of soil mechanics, Terzaghi, an Austrian engineer, fundamentally reshaped our understanding of how soil behaves. Before him, the study of soil was fragmented, relying on empirical rules and simplified theories. Terzaghi brought rigor, systematic experimentation, and groundbreaking theoretical insights. He elevated soil engineering from an art to a true science. His work laid the foundation upon which modern geotechnical engineering is built. Terzaghi's most profound contribution was perhaps the principle of effective stress, introduced in the 1920s. This was a game-changer. He recognized that the stress within a soil mass is carried by two components. Part of the stress is carried by the solid soil particles themselves, through their points of contact. The other part is carried by the water pressure in the pores. Between these particles, the pore water pressure. Terzaghi showed that it is the stress carried by the soil skeleton that governs the soil's strength and its tendency to deform or compress. This concept was revolutionary. Section 6. The Great Squeeze. Understanding soil compaction. Now, let's talk about actively changing the soil to make it better for our purposes. One of the most common ways we do this is through soil compaction. What is it? Simply put, compaction is the process of mechanically pressing soil particles closer together. This reduces the air voids between them, thereby increasing the soil's density. Think of it like packing a suitcase. You press down on your clothes to fit more in, to make the contents denser and more stable. We do something similar with soil, but with much heavier machinery. Why do we bother compacting soil? The purposes are manifold and crucial for construction. Firstly, compaction increases the soil's shear strength. Denser soil can resist greater forces before it slides or fails. This is vital for foundations supporting heavy structures. Secondly, it reduces the soil's compressibility. When soil is compacted, it settles less under load, preventing unwanted sinking or cracking of buildings and roads. Thirdly, compaction decreases the soil's permeability. This means water flows through it less easily, which can be important for preventing water damage or controlling seepage under dams. Section 7. Recipe for solidity, factors influencing compaction. Achieving the desired level of soil compaction isn't as simple as just running a heavy roller over the ground. It's a bit like baking a cake. The right ingredients and the right process are essential for a good outcome. Several critical factors influence how effectively soil can be compacted. Understanding and controlling these factors is key to successful earthwork. One of the most important is the soil's moisture content. There's a magic amount of water known as the optimum moisture content that allows for the best compaction. This is a fascinating interplay. Too little water, and the soil particles resist rearrangement due to high friction. The soil is stiff and difficult to densify. Too much water, on the other hand, and the water itself occupies space in the pores. This water cannot be easily compressed. It pushes the particles apart, preventing them from achieving a dense packing. The optimum moisture content acts like a lubricant. It allows soil particles to slide past each other more easily under the compactive effort, fitting into a tighter configuration. Engineers conduct laboratory tests like the Proctor compaction test to determine this ideal moisture level for a specific soil type. Section 8. Pathways in the dirt, the secrets of permeability. Beyond how tightly we compact soil, we must also understand how fluids, primarily water, move through it. This property is called soil permeability. Think of it as the soil's willingness to allow water to flow through its interconnected void spaces. Some soils are like open highways for water, while others are like a dense, tangled maze. This characteristic is incredibly important in a vast range of civil engineering applications. From designing effective drainage systems to predicting how quickly groundwater will seep into an excavation, permeability is a key parameter. A highly permeable soil, like clean gravel or sand, allows water to pass through it rapidly. This is why beaches drain quickly after a wave recedes. These soils have large, well-connected pores. In contrast, a soil with low permeability, such as dense clay, permits water to flow through it only very slowly, sometimes almost imperceptibly. Clay particles are tiny and flat, and the voids between them are minuscule and often not well connected. This is why puddles can persist for days on clayey ground after rain. Understanding this difference is fundamental for many engineering decisions. Section 9. Governing the flow, what shapes soil permeability. The permeability of a soil isn't a random characteristic. It's governed by a fascinating interplay of several physical factors. Perhaps the most dominant factor is the grain size of the soil particles. Generally, the larger the soil grains, the larger the void spaces between them, and thus the higher the permeability. Think of trying to pour water through a jar of marbles versus a jar of fine flour. The water will race through the marbles but will barely seep into the flour. This is why gravels are much more permeable than silts or clays. The size of the individual particles directly impacts the size of the pathways available for water. Another critical factor is the void ratio of the soil. The void ratio is a measure of the volume of voids, empty spaces, relative to the volume of solid particles. A soil with a higher void ratio will generally have higher permeability, assuming these voids are interconnected. Even for the same soil type, a loosely packed soil will be more permeable than the same soil in a densely compacted state because compaction reduces the void ratio. The structure or fabric of the soil, meaning how the particles are arranged, also plays a significant role, especially in clays where particle orientation can create preferential flow paths. Conclusion: engineering a stable future. From the colossal pyramids that kissed the ancient skies to the intricate network of tunnels beneath our modern cities, soil mechanics has been the silent, steadfast guardian. It is the science that allows us to transform the very ground we stand on from an unpredictable element into a reliable partner in our grandest constructions. The journey from the empirical wisdom of early builders to the sophisticated theories and computational tools of today underscores a relentless human drive to understand and master our environment. This evolution has been marked by brilliant minds like Coulomb, Rankine, and the revolutionary Carl Terzaghi, who chiseled away at the unknown. The ability to compact soil, to deliberately increase its density and strength, has revolutionized how we build roads, airfields, and foundations. Understanding the intricate dance between moisture content, compactive effort, and soil type allows us to engineer stability where nature might have offered only weakness. Similarly, unraveling the secrets of soil permeability, how water seeps and flows through the earth, is critical. It guides the design of dams that hold back mighty rivers, drainage systems that protect our basements, and methods to manage groundwater during complex underground construction. These are not trivial pursuits. They are essential for safety and longevity. The advancements in soil mechanics continue. We now employ sophisticated laboratory testing, in-situ measurements, and powerful computer models to analyze soil behavior with unprecedented accuracy. We explore ground improvement techniques that can strengthen weak soils, mitigate liquefaction risks during earthquakes, and allow construction on sites previously deemed unsuitable. This ongoing quest for knowledge translates directly into safer, more resilient, and more sustainable infrastructure. It means buildings that withstand the Earth's tremors, slopes that remain stable, and resources that are managed wisely. Ultimately, soil mechanics is more than just a branch of engineering. It's a testament to our ability to delve deep, to understand the fundamental properties of our planet, and to use that knowledge to build a better, more secure future. Every stable structure, every smooth road, every dry basement owes a debt to this vital field. As we continue to push the boundaries of what's possible in construction, the principles of soil mechanics will remain the unseen yet indispensable foundation supporting our ambitions. The ground beneath us is not just passive dirt, it is an active, complex system, and thanks to soil mechanics, we are learning to speak its language. As we draw the curtain on this exploration of soil mechanics, it's clear that this field is not just about understanding soil, it's about harnessing its potential to build a better world. The principles of soil mechanics are foundational to civil engineering, guiding the design of everything from towering skyscrapers to expansive highways. By studying soil properties such as strength, compressibility, and permeability, engineers can predict how soil will behave under various conditions and loads, but the story doesn't end there. The methods used to analyze soil behavior have evolved dramatically. Advanced laboratory testing, in-situ measurements, and cutting-edge computer models now allow us to simulate and predict soil responses with remarkable accuracy. These tools enable engineers to design more resilient structures, optimize construction processes, and mitigate risks associated with natural disasters like earthquakes and floods. The applications of soil mechanics extend far beyond the construction of buildings and roads. It's crucial in the development of sustainable practices, such as the construction of eco-friendly foundations and the management of groundwater resources. Soil mechanics also plays a vital role in environmental protection, helping to prevent soil erosion and contamination. As we look to the future, the field of soil mechanics will continue to innovate and adapt. New materials, improved testing techniques, and more sophisticated models will emerge, further enhancing our ability to build safely and sustainably. The lessons we've learned from the past and the advancements we're making today will pave the way for a future where our built environment is not only stable and secure, but also harmonious with the natural world. In essence, soil mechanics is the bridge between the earth beneath our feet and the structures that rise above it. It's a testament to human ingenuity and our relentless pursuit of knowledge. As we continue to explore and understand the complexities of soil, we unlock new possibilities for engineering a stable, sustainable, and resilient future. The ground beneath us is more than just soil. It's the foundation of our dreams and ambitions. And through soil mechanics, we are learning to build a better world for generations to come.